Welcome to my channel. So in this problem, okay, we're given this hot air balloon in which its material alone, okay, meaning it's not fully blown up yet, weighs about weighs 1,000 newtons, and of course plus an additional 2,000 for its passenger cabin. And suppose that the air heated inside, it's actually when you hit, if you have a hot air balloon and you hit it, okay, I think I need to draw that. If this is now our hot air balloon, okay, okay, and if we hit this one, okay, the air inside would be less denser than the air outside, because the air inside is at a higher temperature. Whenever the temperature of the air increases, its density decreases, meaning that uh, the gases inside this hot air balloon would be lighter than outside. So this will actually create the buoyant force. But of course, there's a limit to this volume here before that this can float. Okay, this will only float if the buoyant force will now be able to equate, to reciprocate all the weights, include from the material, the gases inside, and of course the passengers. Okay, if it can now reciprocate that, if the buoyant force can reciprocate that, then it can now float. And if it's greater than, then it can now ascend. Okay, because in order to ascend, the buoyant force must be greater than the weight of this hot air balloon plus all inside it, or all that it carries. Okay, so that there is an acceleration going upwards. Okay, so here it says in the problem that assuming that only 20% the density of this hot air, okay, is only assuming that it's only 20% of the cold air. By the way, the density of the air is 1.293 kilogram per cubic meter. So that means the density of this gas here, the density of the hot air would be equal to 20% of that. So that would give us 0.256 kilogram per cubic meter. Notice it is very light. Okay, so now this hot air balloon has additional uh, load here. Okay, and let's assume that the volume of this is negligible, because in fact, as you can see, the volume of the hot air balloon is very large compared to what it carries. So let's assume that this is negligible, and there's an additional of 5 persons with an average of 75 each. So that would be, the additional load would be 75 times 5. Okay, so what would now be um, the minimum radius of that? Okay, so first let's derive our working equation. Again, our working equation here is that in you have a force downward. Okay, what are the forces downward? Okay, let's I write this in color. The downward forces is the this is now the weight of the balloon. Okay, WB. And of course, you also have now the weight of the gas, of the hot air. I'll just put it WG. And you have the weight of the cabin. Okay. Um, we can actually combine this, the cabin plus hot air balloon, to mean WB. No. Okay. That would be the weight of the hot air balloon is already equal to this plus the weight of the empty cabin. That would be WB. So that would give us 1,000 plus 2,000 plus, of course, the weight of the people, the additional um, five additional persons. So we have now the weight of these persons here, the weight of the people, and this has to be countered by the buoyant force. Okay, so our working equation now would be equal to, okay, from this one, we have the sum of forces along y is 0. So this meaning that uh, FB minus WB, the weight of the balloon plus its empty cabin, minus WG, the weight of the hot air inside, minus um, uh, the weight of the persons must be equal to 0. Here, we are being asked to calculate for the minimum radius. Where can we get that? Okay, notice that we that radius, remember that which among this term will be dependent on the radius. Okay, and of course that would be the weight of the gas, because the weight of this, the materials alone, okay, the materials alone is not dependent on this on actually on the shape of the balloon. Okay, regardless of what is the shape, regardless of the size of this, when you blow this up, that the weight of the balloon, that material will stay at 1000 newton, or that's about 100 kilograms. Okay, it doesn't change. Okay, because it's just the measured weight of the material. Okay, so among this term, what will depend on the radius of the hot air balloon is this uh, weight of the gas plus, of course, the weight of the buoyant force. Okay, because the weight of the buoyant force will depend also on this volume. Okay, and let's assume that this volume again is negligible. Okay, so let's now derive a working equation. What is now the weight of the, what is now the buoyant force? The buoyant force now would be equal to the density of air times this volume. We call this the volume of what we call this, the hot air balloon. So VB, volume of the balloon, or just the gas inside the air, because I use G here. Okay, times G minus the weight of the balloon is just equal to, this is just easy, that's 1000 plus 2000 newtons. So that would be minus 3000 newtons. Okay, minus the weight of the gas. What is the weight of the gas? That would now be the volume of this. Okay, by the way, that's the density of the gas inside. Okay, this density is actually that density there, the hot air, times the volume of this gas here, minus the weight of those 5 people added. So that would give us 75 times 5. That would be 375 375 kilograms times 9.8, 3675 newtons, and this is equal to 0. From here, now let's assume that this is a perfect sphere, although a hot air balloon is not actually a perfect sphere, but of course it will be difficult to solve that geometry there. So let's assume that this is a perfect sphere, okay, such that the radius is uniform all throughout. Okay, so we can now factor this one out. This has values. Okay, we can transfer this one there. So you have now density of air times Vg. Okay, um, uh, times G minus. Okay, there's a minus here. Okay, minus rho G Vg equals 6,675 newtons. That would be the sum of this. I have moved it here. And from here, we can see that Vg is just equal to, I'll factor out Vg first. Vg, that would be rho air times minus rho G times G equals 675 newtons. So from here, the volume is now equal to 6675 uh, over the density of air minus the density of the gas times G. But this VG, since this is a sphere, this is equal to 4 thirds pi r cube. So from here, we can see that our r now is just the cube root of this one. Okay, if we do the algebra, okay, that would be equal to, meaning that you have to divide it by this one. So you have now 3 over 4 pi over 4, 3 over 4 pi times, that would be 6,675 over the density of air minus the density of the gas, the hot air times G. And that would be, this is raised to cube 1 over 3 cube root. Okay, now I can now put all this, because this is the density of the air is just dust. All the units are actually now compatible. This is in newtons, this is in kilogram over meter cube. So all of these are now incompatible, that they are now compatible in terms of units. Okay, so whatever this one is, the unit will be in meters, because this whole thing here is meter cube. So this will be in meters. Okay, uh 3 times 6675 over, you have 4 times pi times the density of the air, which is 1.293, minus the density of the hot air, 0.2586. Okay, close parenthesis, times 9.8. Okay, yeah, I think this is okay. And if we do this, okay, let's maybe review the formula so that we can be sure. Okay, okay, that would be 100. This whole thing is 157 point 2, okay, cubic meter. But we have to take the cube root of that, so meaning we have to raise this into uh, cube root of this, of the ants there, and that would give us 5.39 meters. Okay, so the answer now, this will give us 5 point uh 5, around 5.40 meters. Okay, okay, so that will now be our radius. Okay, meaning that by diameter, our hot air balloon is about 10 meters, more than 10 meters. Okay, so this is actually not a complicated problem, but somehow you need to analyze it in order to understand it. Okay, that would mean that this is the minimum. In order for you to float, okay, let's analyze this much further. In order for this to go up, because this is just when you reach this radius, meaning that the hot air balloon will stay put. I mean, it will not go down and it will not go up. Okay, but if you take a larger radius than this, then that hot air balloon will start going up, because what happens when you have a greater when you have a radius greater than here, this buoyant force now will be much greater than the sum of this, all of this one, the sum, all of this. Okay, if this buoyant force is greater than the sum of these three w's here, the three weights, then it will start to go up, it will start to accelerate, it will have a positive acceleration. Okay, the greater is the difference, the greater is the acceleration. Okay, that's why in order to go up, you have to uh, uh, I mean, it has to expand. But there's another. Okay, the video was actually cut off, and I didn't notice this until some time. But anyway, here I have to repeat it again. But okay, let us study a limiting case here. We want to ask. Okay, maybe you are intrigued. If the buoyant force becomes larger and larger, then this will accelerate. Um, this can actually accelerate, I mean, indefinitely. But that is not actually the case. And in fact, in reality, in the more practical, yeah, in the more realistic case, the size of this of the balloon, it has a maximum size, okay, up to which it can expand to, okay. And okay, let's just assume that this is not the maximum size, okay, that it can expand to, meaning that the manufacturer of this material was able to already to calculate this one, given the load, the maximum load, and so on. Okay, let's just assume that this is the maximum weight, but if I mean the maximum radius, but if this is the maximum radius, notice that this is just in our solution. This is just the minimum required radius to give us a buoyant force that is just about to counter these three weights, okay, meaning that having this radius, our buoyant force is just enough to counter the weight of this. It will not go up and it will not also go down. But if we want to ascend, we must we must actually increase the buoyant force. But if this is the maximum size, then we could no longer increase the buoyant force. We could no longer change it, okay. And of course we could not, assuming that then we will not change the number of passengers and this weight here. So meaning all these three, FB, WB, the weight of the balloon plus the cabin, and the weight of the persons, the passengers, um, are no longer, we could no longer change them. We could no longer increase or decrease them. But what we can do is actually with this, with the weight of the gas, or the hot air. Why? Because actually here, in the problem, I just say that it's 20% of the air, of the cold air outside. But in reality, actually, the more you heat air inside, the lighter it becomes. And okay, once it becomes lighter, then this WG will be smaller. And for a specific WG, in our case, if it is 20%, this is equal to zero. But if this decreases to, let's say, 10% or even lower than that, then this will no longer be zero. Okay? It will give us an upward acceleration. Why? Because this whole thing here will be less than the buoyant force, the sum of these three weights. Okay? Uh, Here I wrote some temperatures here before, right after the video was cut off. Okay, uh, it's just as assuming. For example, if at 30 degrees Celsius air outside and the air inside the gas is 80 degrees Celsius, let's say it's 20%. If we increase it to 90 or to 100 or whatever temperature that we wish to, of course we could not. I mean, there's a limit to that. But let's just assume that there's no limit. Then this will even further decrease. This will decrease much further. Okay? And decreasing this will decrease G. And decreasing G will actually uh, cause an acceleration here. So let's solve the limiting case, meaning our limiting case now would be, okay, let me write that equation again. FB minus the weight of the balloon plus the cabin minus the weight of the persons, or the passengers, minus the weight of the gas, and this is equal to, this was zero. But then, if I'm going to decrease this gas, okay, this will no longer equal to zero but be greater than zero. This will be equal to MA in favor of the upward force, because when this decreases, our buoyant force is clearly greater than this. Our buoyant force will no longer change because since our radius is fixed, okay, this is already the maximum size, so the buoyant force doesn't change. But what actually the driver of the hot air balloon would do, or the pilot, would actually hit the gas. Okay, hit the gas even much, even at a higher hit the gas at higher, at yeah, at higher temperature, in order to decrease this, the weight of the gas. Okay, and decreasing this will actually increase the temperature. I mean the acceleration. Now let's the limiting case of this is that as we heat the gas to a higher and higher and higher temperature, this will decrease and decrease and decrease. And assuming that we can raise the temperature to whatever temperature that we want. Okay, of course not in reality, but let's just let's just accept that for a while, for our limiting case. That means that this will approach to zero. Okay, this will approach to zero as the temperature of the gas increases. So that means, okay, we take now the fastest possible upward acceleration um, we can have with this setup here, with the max our maximum radius is 5.40. So that would just be FB minus the weight of the balloon plus the cabin minus the weight of the passengers over the, what is this mass? The mass here will be the mass of uh, the cabin plus, yeah, the mass of the balloon plus the cabin, the materials, plus the mass of the passengers. Okay, so we have this value. We already have this. MB is just equal. Notice that WP W WB plus WP. I mean WB is just equal to 1,000 plus 2,000. That would be 3,000 newtons. Okay, and we divide this by 9.8, so we obtain this MB. Okay, so we can now calculate this acceleration. It's just equal to, what's the buoyant force? Let's calculate the buoyant force again. That is the density of the air times the volume of the balloon. Okay, the volume of the gas times G minus, this is 3,000 newtons, minus, this was, what was this? Uh, 3675 3675 newtons over, that would be uh, 3,000 over 9.8 plus, this was the weight of the mass of all the passengers. That would be 375. Now, of course, the density of the air, okay, what was the density of the air? That would be 1.293. 1 point, okay, so let's calculate this. This would be 1.293 times the volume of the balloon, which is, again, that would give us 4 times, uh, 4 times pi times the radius, the maximum radius, which was 5.4 cube divided by 3, and then times 9.8. That would be this, minus 6675, sum of these two, over, okay, that would be 3,000 divided by 9.8, the mass of the cabin plus the balloon material, plus 375. Okay, and that would give us 2.47. Our largest possible acceleration upwards would be 2.47 meters per second squared. This is our fastest, I mean, yeah, the largest possible upward acceleration. Okay, because I mean, it cannot actually, it is bounded. Okay, we cannot go up, we cannot go up as fast as we want to. Okay, and the fastest that we can actually go up is at the rate of, when we accelerate at 2.47 meters per second squared upwards, and that would be equivalent to very, very, very hot air, such that the weight of the gas, okay, of the hot gas would be equal to zero. But we know that it cannot be zero, meaning, let's put a limit here. This one, our acceleration would be less than 2.47. Of course, assuming that the least value that we can have here is zero. Okay, so this is the fastest, I mean, yeah, the greatest acceleration we can have. That's an upward acceleration. Okay, so yeah, thank you for watching, and if you have not subscribed yet, please subscribe to this channel, because most of the problems I solve here, and I think so far what the problems I have given in my channel are, I mean, yeah, are my original problems. I make the problems Okay, you cannot find these problems anywhere, but of course there may be some similar problems out there in the books or on YouTube. Okay, but at least the problems that you're going to encounter here are my original problems. I'm making my own problems. So that's more reason for you to subscribe in my channel, and also to help me grow this channel. Okay, thank you. See you again the next video. We'll have more videos to we'll have more problems to solve.